Okay, so let's take a look at cyclohexane. Notice that I have a cyclohexane molecule here, and what I've done is I've put all of the ones that go up and labeled those with red, and we have things that are around the center. Those I put as white. Now, there are different ways or configurations that we can look at cyclohexane. From the top, you can't really see much, right? That just looks like a sort of a ring. But there's two major conformations that we can look at here. So this is actually the chair conformation. So what I have here is I have like 4 different carbons sort of in the middle, making a sort of a square. And then I have one carbon going down on this side, and on the opposite side, that's going up. That is more energetically favored than if I have what's known as the boat arrangement, which looks more like this. And here's why. Those two things kind of bounce into each other. But notice here, it looks like we've got a little bit of a boat. So the 4 like squares are in the middle, and then we have things going up on both sides, okay? So this chair conformation is much more frequently used, and the reason why is because it's energetically favored. We've got atoms that are more spread out, and they tend to be happier that way. We can look at this in a number of ways. We can look at it from the side like this, or we can look at it kind of like this. And what that does is it gives you almost a Newman projection on this side as well as this side, so that you can see sort of down that bond. And what we would see really quickly there is that you almost, if you had something large like a carbon back here, that would be a gauche interaction with what we have like up here. Or any type of axial position, so things that are pointing up or down. So if we have one like right there, that's going to give us a gauche interaction with this carbon back here. So there's different ways to sort of view this from, okay? As I was saying, the axial positions are the ones that are in red. So those are things that are pointing up or down. And notice that we have an alternating type of pattern here. So here we have a carbon that's pointing up in the chair direction, and that means the axial position is up. And then if I move forward, this is pointing downwards. Like, see how that angle makes a downward point? That is pointing down. The axial position is pointing down. And this sort of alternates. So next we have one up, it's pointing up. Next we have one down, it's pointing down. And so that's sort of how to sort of see these a little bit. The opposite's also true. We have here a carbon with the axial position down. That means that the equatorial position is here. We call that equatorial because it's like on the plane or the equator of the molecule at that point. So if you've got an axial position going up, then the equatorial goes slightly down. If we have an axial position pointed down, then we have an equatorial slightly up. Now, when I flip these, what I do is I take 2 opposing sides, okay? And I brace the rest of the molecule because there's some strain that's introduced. And I move the one that's up, down, and the one that's down, up, and we kind of flip things just like that. And notice what happens. Now all the ones that were on the equatorial position flip up to, or down, to the axial positions. And those that were on the axial positions are now in the equatorial position, right? And so that's sort of what's happening as the rings flip. They go back and forth. And you go through some crazy in-betweens that are like twist boats and half boats or whatever you want to call those. And in truth, that's really what you're doing. These are much more stable in the chair position than they would be in the boat position. Okay, so now let's take a look at notes and see if we can understand that in a 2D format rather than a 3D format. But the next thing I'm going to say is please, please, please try this with a model kit so that you understand what's going on. Okay? Okay, so this is what it looks like in 2D or written on a piece of paper. The boat configuration, you can see, goes up on both ends, and so that's supposedly making a little boat down here that doesn't much hold water because we don't actually use that form. Instead, what we use is the chair formation, and I think that you can see why. These hydrogens are more spread out, and so are those down here. Versus up here, you would have these two kind of running into each other. And notice that I've got that written in the Newman projection form. Those are all eclipsed there versus we have a staggered arrangement in the chair conformation. So we call those things that are pointed upwards axial, or those that are pointed down as axial. So those are the ones in the model I originally had as red. And then we have those that are the equatorial positions. So notice that those are kind of in line with the plane of that chair molecule. And as I was showing you with the model kit, when things flip, whatever is axial becomes equatorial and vice versa. So here's what you do on paper. We take opposite carbons. This one moves up, this one moves down. So that we have 5, 6, 2, and 3, sort of that I've drawn there, that kind of just still stay stable, right? So that's sort of like the square that you saw before, that sort of just, they shift back and forth, but that's still sort of the stable foundation. That is a difference between a flip and a rotation, so make sure that you are actually moving opposite carbons that are at the tip of the chair and at the bottom of the chair and flipping them when you do that in 2D. So looking at a chair conformation, we have to kind of figure out what's going on when we have a substituent. Substituents that are not hydrogen are obviously going to be larger than hydrogen because hydrogen's the smaller atom that we have. So let's look at the two options. We could either have a larger, whatever it is, substituent right here at the axial position, or we can have it at the equatorial position. So if we have this at the axial position, then what that means is we now have a gauche interaction between these two locations. So this is looking at things sort of like in the Newman projection, okay? But you can also see this by making a model kit. You can see that this larger thing ends up interacting with the two other axial positions pretty easily, okay? So what ends up actually happening is that we don't end up with this larger thing on the axial position. We instead have that on the equatorial position. Here's why. There's way more space. Look how much more space this thing has. Look at all that space here versus, see how many interactions it has over here? So since we can have more space in the equatorial position, larger substituents, larger than hydrogen for that matter, really would prefer to be in the equatorial position and are that formation a vast majority of the time. So that's something to note. When we increase the number of substituents on a ring, we certainly want to keep as few as possible in the axial position. This interaction that we have here between that larger substituent and the other axial positions are called 1,3 diaxial positions, or diaxial interactions. These are quantifiable. There are several charts out there where you can quantify those numbers. Essentially, the larger that item gets, the more it tends to interact with other types of hydrogens, and you get more steric hindrance. So if you have 2 or 3 substituents, you definitely want to keep as many on the equatorial position as possible because that's just closer to reality. And again, we can quantify that if need be. If you have substituents that need to be in both the axial and equatorial, you probably need to quantify that to determine which position would be best for that particular molecule. Another thing to note while we're here talking about rings, there is something called an Haworth projection that we use sometimes, mostly in biochemistry, but in other things as well. And notice that this is not going to give an accurate viewpoint of what cyclohexane kind of looks like, because it shows that we've got like this area right here is coming towards you, right? But it's showing that the hydrogen and the chlorine go up and down. That's not exactly true, right? We just saw that one is an axial position and one's equatorial. This just clarifies it for your viewpoint in 2D. It's not giving you a 3D accurate type of representation. But we can use this to look at different types of arrangements of that molecule. So when we have two chlorines that in this case would be on the same side of the plane of where that cyclohexane ring is, we would call that a cis. And when they're on opposite sides of the plane of the cyclohexane, we refer to that as trans. And so this will help us with naming as we enter the next subject. Thanks, and hope this helped.